Hello, my name is Brian Hansen, and this is my tutorial for Project 1. So to start off, you're going to want to drag Fluent onto the project schematic to create a standalone system, and then double-click Geometry to open SpaceClaim, which is the design software we're going to use to model it. Alright, so once SpaceClaim's opened up, you're going to want to go down here to this little view cube and click the Z-axis to correctly align the axes, and then you're going to select new sketch plane and make sure you are now doing the XY plane because that's the axis in which you're going to create the surface. So from here, you're going to want to start, well, first you're actually going to want to go to File, SpaceClaim Options. Going to want to go to Units and make sure that it is imperial and inches. This is not a permanent change, but it's something that we need for right now in order to correctly set the right dimensions for the wind tunnel since it's in inches. So to begin with, you're going to want to draw 3 lines on the left side of the axis. This will delineate the settling chamber and the contraction chamber in the beginning of the test section. And then on the other side, you're going to want to create 2 lines which delineates the other side of the test section and the diffuser. So from here, you just want to generally connect the lines. Doesn't have to be like perfect right now, because we're going to use constraints to make it precisely what we want. So from here, first thing you might want to do is use the symmetry constraint and actually use it to make sure that it is symmetric across the x-axis. Then you're going to want to use the symmetry constraint around the y-axis to make sure the test section is centered. Now from here, there's really nothing else you need to change, except now we can start setting dimensions. So for the settling chamber, it has a height of 22 inches. And it has a length of 15 inches. I'm actually going to use the move tool to We're going to use the move tool to move this out of the way so it's not screwing up everything. Then we've got the length of the contraction chamber, which is 24 inches. So now we're going to set the dimensions for the test section, which is a height of 6 inches and a length of 12 inches. And then the length of the diffuser should be 42 inches. Now to make sure that we actually get the angle right for this diffuser, I'm going to use a construction line, which is not going to actually contribute to the sketch, but is just a reference line that I can use to set this dimension. And that should be 3 degrees. Okay. So once we've done that, the next step is to actually delete these inner edges because they're not going to actually be in the final surface or else they would get in the way. After that, some dimensions are actually going to disappear because they're dependent on that. So I'm just going to set them again. They're already set, but Just need to make sure that they're there. All right, so from here, well, this might not be necessary just for the sake of making sure everything's back in the same units. I'm just going to reset it back to metric and put it into meters since that is units we are going to be using. So we're going to finish the sketch and turn it into a surface by hitting End Sketch Editing up here. And that is our sketch, so that's done. So from here we can close out and go back into Workbench. So now we're going to double click on Mesh, which is going to open our meshing program. All right, so once meshing's open, we're going to do the same thing we did in Space Claim and go down to this little viewpoint and click the Z-axis to make sure it's aligned correctly. So now over here by Mesh, we're going to right-click on it, Insert Method. From this method, we want to make sure that our geometry is selected, so you click it and then you click this little Apply Selection button to make sure that the body's selected. So on this Details tab down here, you're going to click the method and switch it to Triangles. You're going to go back up to Mesh, and then you want to make sure that the element size is 0.007 meters. Now from here, we should be able to put a mesh and then update, and this should mesh out the wind tunnel. And there we go. You can see, if I zoom in, you can see all the meshes, all the little triangles. So this wind tunnel is now meshed out. So from here, we're going to actually hit Control E. That's going to go into edge mode, because now we're going to want to actually name the different edges. So for this one, if you hit N, you can create a new selection name. So from here, we're going to call it inlet, since that is what that represents. On the back one, we're going to hit N again. We're going to call that outlet. And then if you click and then hold Control and continue clicking, you can select multiple edges. So we're going to select all the edges of the wind tunnel that is not the inlet and the outlet. From here, we're just going to hit N and call this tunnel wall. And if you go over name selections, you can see, if I expand this out, you can see inlet, you can see that marked correctly, outlet marked correctly, and tunnel wall is all marked correctly. So from here, you can go to File, Save Project, just make sure it's all saved. And then once it saves, you can exit out and go back into Workbench. So from Workbench, you want to right-click on Mesh and Update to make sure that that step is updated. Okay, so once meshing is done and it's updated, double-click Setup to open the actual physics software we're going to be using. So from here, you want to ensure that double precision is selected, and then you can start it. Okay, so it looks like everything's loaded in now. And just to make sure everything's working properly, I want to hit Report Quality and check, just make sure everything's working. Okay, so now we're going to begin setting up the physics for the system. We want to go to Models, Energy, double-click that. I'm going to check this, make sure energy equation is set. Now we're going to select Viscous, and we're going to select K epsilon, enhanced wall treatment, and pressure gradient effects we're going to check. And we're going to hit OK. Now under materials, we're going to select fluid and then air, double click. So there's nothing you need to change here, just hit change create, so that'll create the fluid, the proper fluid that we're going to be using, which is air. So now that's set up, we're going to set up the simulation parameters. So we're going to go to boundary conditions. This will open up, you'll see the different things we named in the other program. This interior FFF surface is the actual surface that lies within. So the only thing we really need to change here is inlet. Now we're going to hit edit to open up its settings. For the first frequency, 10 Hertz, the first calculated velocity for the inlet came out to be 0.58 meters per second, so that is what we're going to input for velocity magnitude. We're going to apply and make sure for the outlet as well that gauge pressure is set to 0, which just means that the total pressure sitting outside of the outlet is 0, which is equivalent to atmospheric conditions, which is what it should be. That you don't have to change anything. So now from reference values, we're going to compute from the inlet. That's our starting position. And a reference zone, we're going to click FFF surface, so that's the actual zone that we're referencing. Now down under initialization, we're going to initialize it just to make sure it's set up properly. It's okay if you get this little warning down here. Doesn't mean it's not going to work. It's just a check. Then we want to go down to run calculation. We're going to set the number of iterations to 300. Once that's set, we are basically done on everything. We just need to compute it. So I'm going to hit calculate and let this run and compute. So it appears everything worked pretty quickly and correctly. So let's check to make sure everything works. So if we want to actually get some plots and contours from this, first thing we'll do, let's come down to contours. We can double click on contours. I'm going to make a new one. I'm just going to make a velocity contour just as an example to show what that looks like. Name it velocity. Do contours of velocity, and we're going to be looking at velocity magnitude. And we want to look at the contours for everything. So I'm going to save and display that. And if you zoom in, you can see this is the velocity contour, which makes sense. And here's a scale. So it shows that the velocity increases as it gets into the test section and the decreases as it comes out, which makes sense. And you can see that it's really low, practically 0, if not 0, at the edges, which makes sense because of the no slip boundary condition. So that's how contours work. You can use that for all different forms of pressure as well. Now, if you want to actually plot things, before we plot anything, we actually want to have a path to plot on. So we're going to, I believe, come to results and then surface create. We're going to create a line / rake. So we're going to want to actually plot along the center line directly in the center of the wind tunnel. So I'm just going to call that center line. And we actually want to set the endpoints of this. Now I'll have to double check to make sure I know, because it was in inches originally, so we'll have to see, assuming 0 is at the test section, because that's what we set before. I'm going to double check and convert inches to meters to see what the actual length of this line should be. Okay, so this left one should be negative 1.143 meters, and this right one should be 1.2192. So we're going to create that center line. That's basically going to cover the entire wind tunnel. So we've created that surface, and then down under plots, under XY plots, we can create a new XY plot. For this, I guess I'll plot dynamic pressure. So we're just going to call this dynamic pressure center line to indicate that we're plotting against the center line. So we've already got pressure selected. We're going to do dynamic pressure, x-axis functions, direction vector, that's fine. And then we're going to select center line as the only surface we're going to be plotting on. We're going to save the plot. As you can see here, this is the dynamic pressure, which makes sense. As you get closer to the center of the test section, dynamic pressure should increase along the center line and then decrease again. And it's going to be at its lowest at the inlet, which is where the static pressure is at the highest. So if you also wanted to actually, if you want to actually plot vertically along the test section, you would want to create another line rake. You're just going to want to set the Y values this time because we're going from down to top, and converted from, since it's 6 inches tall, it's 3 inches down, 3 inches up, which is 0.07 meters down and up. So we're going to create that. I guess we'll just call that vertical center. I'm going to create that. So under surfaces, should say, I'll just choose the vertical center for that. So if we create another XY plot, this time I'm going to plot velocity again. just to show correctly. For if you're actually doing the y direction, you have to change the plot direction to 1 for y and x to 0. This is because it's kind of like a vector that gets multiplied by it. So if y is set to 0, you're not going to get any good results. So now that it's set this way, it should actually graph properly. And we're going to select vertical center, and we're going to say plot. Now you can see less points makes sense because less of a length, but you can see there's a little velocity point down here at 0. You can see basically this is outlining the boundaries, the boundary layer on either side. If you're imagining this going across, you can see this is the velocity profile at the test section. So that basically concludes one case of 10 hertz. If you want to do 30 hertz and 50 hertz, you just go back in to boundary conditions inlet and change the velocity magnitude and then rerun the calculations. But that should be all.